Welcome to the third unit of the third week in the OpenHBI course Parallel Programming Concepts. In this unit we want to talk about task parallelism and programming models and ideas that go beyond the basic idea of OpenMP as presented in the last unit. A first example for task parallel programming beyond OpenMP is the Silk language. Silk is a derivation of the C programming language with several new keywords, and this is a true language extension in comparison to OpenMP, where we mainly had compiler instructions formulated as pragmas. Silk is a comparatively old approach. It was developed at MIT and is maintained since 1994. And meanwhile, Silk has a commercial version produced by Intel called Silk Plus. And this is interesting because if you live in the x86 world and you want to do parallelization on these kind of systems, then Intel Silk Plus is one of the interesting possibilities to deal with task parallelism and parallel programming on a comparatively high level, while still being in a native language. Silk has support for different platforms such as Windows, Linux, and macOS, so you're able to write portable C code as long as you rely yourself on the Silk keywords and the different libraries that are available in a portable fashion. Silk has the concept of serialization, which is a novel thing in comparison to other approaches. The serialization approach says that whenever you take a given Silk program and you remove the Silk keywords, you end up with a C program that has serial execution semantics. And the promise is that the semantics of the program execution, the control flow, does not change when you remove these keywords. So whenever you have the parallel or the serial version with or without the Silk keywords, the control flow semantics remain the same. So the keywords are designed in a way that you are able to achieve this goal, which hopefully gives you a better trust in the behavior of your code when it comes to concurrent execution. In Silk, we have three basic keywords to express potential parallelism. The first keyword is Silk spawn, which implements an asynchronous function call. So the idea here is that you tell the runtime system or the compiler, I have a function call here and please execute this function call asynchronously, maybe as part of a task definition, which is then mapped to a thread. The runtime decides if this is a good idea or not. So if your execution resources give you enough capabilities in order to have a true parallel execution, otherwise the function call is just executed in a serial fashion and then returns with the result value. Silk sync is the second keyword, and this allows you to wait until all spawned calls are terminated. This is more or less a barrier implementation again, where you are able to declare that you want to wait until all the concurrent tasks that run now in your system are finished, and then you want to continue with your execution. The more interesting aspect of Silk sync is that it also works for recursively created tasks. So whenever a function that was spawned by Silk spawn itself again spawns new tasks, then Silk sync will also wait for these tasks. So when you have recursive implementations, for example for a tree search, you can easily synchronize with the termination of all these activities by using a single keyword. The third primary keyword in Silk is Silk for, and this is comparable to the loop parallelization approach in OpenMP. So Silk for allows you to declare that the following loop should be executed in parallel. The loop iterations should be chopped up into different chunks, and these chunks are then executed concurrently by a couple of tasks, and if you have the parallel resources, they are mapped to it. Besides the basic primitives for concurrent execution and task definition, Silk has also advanced support. Since it extends the language, it has more possibilities than OpenMP to work with the idea of task definition, implicit task definition. One basic point is the new array operator, and this array operator allows you in Silk to define concurrent activities on a set of data. This is something that is also called data parallelism. When you remember our discussion of the SIMD paradigm, this is basically the same direction. You take a couple of data items and now you want to apply the same operation to all of these data items. When you want to express such an activity, you typically have to do this in an explicit way when you work with threads or OpenMP. In Silk, you can have an implicit way of expressing the parallelism here. You see a couple of examples. For example, the first example is a shorthand notation for a loop that goes over the different array items and assigns the value 5 to each of the items. And with such an expression of a data parallel operation, the Silk compiler and the runtime are now able to parallelize this loop work that you expressed there. So instead of declaring a for loop and making it parallel explicitly, you just write down a more high-level notation, and then compiler and runtime can decide if parallelization makes sense or not here. You see that there are further examples how to deal with this idea, so you can have not only a lower bound and a length, but also a stride in order to skip some of the items in your assignment. Or you may assign one array to the other, or you may even want to do parallelized function calls with the elements of this data array. So Silk has a lot of different options how to deal with this idea, and it basically gives you a more high-level declaration of how concurrency should be done inside your application. Another example from the zoo of available abstractions in concurrent and parallel programming is Intel Thread Building Blocks, Intel Threading Building Blocks, TBB. This is a portable C++ library, and it is intended to further extend the functionality of OpenMP and Silk with more high-level constructs. So you have the already known loop parallelization idea, you have synchronization support, you can spawn tasks explicitly, but beside that, you now get also so-called concurrent containers, so you get data structures that are already implemented in the way that they can be used for multiple tasks and threads. This demands some kind of synchronization support and maybe also the consideration of caching to deal with the memory wall. But in libraries such as Intel TBB, all these problems are already solved. So the crucial aspect here is that you get an even more high-level abstraction from the basic concurrency problems we talked about last week. You can simply use these data structures from your parallel activities without even thinking about how to deal with race conditions in the management of your shared data. Intel TBB has also something that is called an unfair scheduling approach. So whenever you work with tasks in TBB, it will prefer the solution to the memory wall by, for example, doing clever caching or prioritizing particular threads in order to use caching effects instead of making sure that all your tasks get an equal share of the resources. So unfair scheduling means that instead of the operating system approach where all processes and threads are treated equally, we now get into a solution where we want to explicitly deal with the memory wall problem by aligning the scheduling of tasks to threads according to caching issues and other optimization criteria. If you want to look into the Microsoft world, there's something like the Microsoft C++ concurrency runtime library, which more or less fits the same purpose as Intel TBB. Here's an example for DBB code. This is C++ code that is intended to compute the Fibonacci number. Fibonacci number is computed recursively by taking the Fibonacci number until n-1 and the Fibonacci number until n-2 and adding them. So you see that this is an inherently recursive problem, and in TBB you have different high-level primitives that allow you to express such a parallel recursion very easily. You see here the allocate child operation, which is defined as part of the task class, and this allows you to define that you now want to run a concurrent activity. The TBB runtime library will then decide how to deal with that in terms of tasks and threads. You just declare that you want to have a concurrent activity here, and then you rely on the management capabilities of the implementation to actually parallelize this to your particular execution resources. You also see that there's an explicit spawn statement and combined spawn and wait statement. So there are different ways of starting new tasks and letting them run. It's all object-oriented, so it relates to C++ only, which gives you the chance to work with high-level abstractions in your parallelization. Another example for the capabilities of TBB and similar libraries is in this example. So here you see that we have concurrent vector definition. This is part of the library, and our vector, by using this type, is then able to deal with concurrent access from different tasks at the same time. So the synchronization is built in, and you see now that by this we can basically fetch values from the vector in order to see if a particular value was already written. And if this is not written in this example, then we use the so-called yield statement. So we voluntarily give the control of execution to another task, because we know at this point in the execution flow that we no longer can do any reasonable work. So the message in this example is that with concurrent collections, like concurrent vectors, concurrent sets, concurrent hash maps, you are simply able to access values, read and write values from different tasks at the same time without doing any kind of synchronization by yourself. The sheer usage of such concurrent data structures gives you the safety that no race conditions can occur in the internal management of these data structures. When you want to go a little bit higher to manage languages like Java and C#, the question is, do we have the same high-level support for concurrency also there? And the answer is yes. Meanwhile, for a longer time, since Java 5, for example, in the Java world, we have support for abstract definitions of tasks. This is implemented by so-called executors. So the executors executor objects are able to take objects that implement the runnable interface, and this is the representation of a task definition, and they can then decide how to deal with these tasks, how to schedule them to threads, how to run them. There are several default implementations in the Java class library, for example, the thread pool executor, which takes a given pool of threads and then maps the defined runnables on the given number of threads. There's further support in the Java library for futures, for example, where you can call or start a task and then get back a future variable immediately that allows you to have a handle for a future upcoming result. We talked about this last week. So in Java, also in .NET and in the other high-level languages, we meanwhile see that high-level primitives, high-level collective data types are commonly supported, and it is always a good recommendation to rely on these data structures for your parallel application instead of doing manual thread creation or even manual task synchronization in OpenMP, because if you rely on the knowledge of other people already implementing such a library, you may be faster with your own code. You see here a couple of collections. It's also referenced in the related readings, where you have the class libraries of, for example, .NET or Java util concurrent, and these class libraries have a large set of concurrent data structures available, so you don't have to deal with that issue anymore. You just use the right kind of data structure, and then hopefully you can express your parallelization attempt in your code without the problem of producing race conditions in the shared data access. If we take now these high-level approaches and somehow see this as an extension of the classical task model, one interesting question could be, can we even go further? Can we even go more abstract and start to no longer even think about parallelization and concurrency in our code? We just write it down, and all the management of concurrency and potential parallelism should all be done in the runtime system. How would that be possible? And there is a surprisingly old answer with functional programming. Some of you may already know that. Functional programming is a different approach to the so-called imperative programming. So instead of writing down a control flow where you state in your program, first do this and then do that, you define your program as a sheer collection of functions. These functions are intended to be side effect free. Side effect free means that the result of a function only relates to its input values and nothing else. This actually means that there is no shared state between these different functions. They all only rely on their input values, and the chaining of these different function calls then at the end leads to the result of the application. The foundations for this idea are surprisingly old, as I said. For example, they lie in the lambda calculus from the 30s and in the Lisp programming language from the late 50s. If you have this situation, so if you're able to write side effect-free computations in the notion of functions, then you come into a situation that you have no longer shared state between the different functions. If you have no shared state between the functions and you have different functions that are executable at the same time, then you can run them in parallel without thinking about that, because the side effect freeness makes sure that there can be no race condition or any kind of situation where the ordering of the execution becomes relevant. So race condition situations you have to protect yourself from are less probable in functional programming if you do it in a pure fashion, because because you get rid of the shared state problem we discussed in the second week as part of the concurrency problem declaration. So functional programming is a nice approach to deal with concurrency issues and shared memory parallelism. The counterside is that this is a programming model that in its purest fashion is not very much liked in the developer community. So what we see now is that some of the functional programming constructs start to move into the classical programming languages, such as Java or any other language. So instead of converting all the developers to functional programming purely, we now see that the compiler developers and the toolkit developers more and more give us functional programming style constructs in our beloved languages, and this allows us to use the idea and the advantages in our own code. So here's an example from the famous Joel Spolsky about the difference between imperative and functional programming. Let's say we have the piece of code on the left side where you can see that we have 2 times a function call only with different arguments, and then again the same situation with a different function. But at the end what we really want to express is that we perform this different kind of operations with the cooking primitive. And the idea we apply in order to make that a little bit more pretty and a little bit more manageable is the idea of a higher order function. So in a higher order function, you declare a function that can have a parameter where the parameter itself is a function again. So you can hand over functions as an argument to another function, and this allows the called higher level function to use that functionality with the given data items. You can see here the very primitive example that we actually call the cook function with the put in pot and the boom boom function, and then both times the same kind of activity can be done based on the handed in functionality. This works only if we have side effect free definitions, so the functions that are given into the higher order function must be side effect free, so they should only relate on their input parameters. But if this is the case, then we come into the situation that the higher order function, in this case the cook function, can execute, can organize the execution in whatever way it wants. It can define concurrency, it can run the stuff in parallel, because the functionality that is given in is side effect free, so we no longer have the problem of dealing with synchronization or any kind of ordering constraint. When you have such a concept, higher order functions, what comes also in very handy is the idea of anonymous functions. So we now want to hand over functionality, function definitions as part of a higher order function call. In this case, again, the cook function. But here we no longer relate to a function that is defined somewhere else, but we define this function implicitly as part of the call. You see this here in the lower right example. This is what some languages call a lambda function or function literal or an anonymous function. So this is basically a syntactical tool to allow you more condensed code. And again, it gives you the possibility to get implicit parallelism, because the higher order function can now use this defined functionality in whatever way it wants, for example, by mapping it to different tasks. So functional programming is like the highest level of abstraction that goes beyond task parallel programming when we talk about parallelization in shared memory programming. We need the idea of pure functions then, because this execution should have no side effects. And since this is such a handy concept to express potential parallelism without explicit task and thread spawning, it's meanwhile common in a lot of languages. So if you look into approaches such as Clojure and also parts of Scala, you find functional language constructs there, but also more specialized functional languages become interesting for more developers today, such as Erlang or F#. So if you intend to use these ideas in order to express your parallelism in a shorter and more implicit way, then please check your favorite language if it supports, for example, map or reduce patterns. This is something we will also discuss in week number 6. These are all things that rely on the basic idea of higher order functions and side effect freeness. And this is the perfect foundation for implicit parallelism, where we completely release ourselves from the definition of concurrent activities. Instead, we write our code in a way that given runtime system or language compiler can completely dedicatedly decide in a dedicated way how and which of the tasks should be parallelized on the given set of processing elements.